Section 1 Introduction. In this introduction, we're delving into the world of systems that interact with graphical user interfaces, GUIs, to accomplish tasks, which could be beneficial in automating mundane tasks, enhancing accessibility, and broadening the capabilities of digital assistants. Earlier research primarily centered around the use of structured representations of these user interfaces and custom representations for specific tasks. However, these structured representations aren't always accessible, especially in instances such as web applications that heavily rely on scripting, restricted environments with limited DOM access, and mobile apps that usually don't reveal their underlying structure. Moreover, even when we have access to the source data of the structured applications, it's often difficult to decipher due to obfuscation and discrepancy with the visible GUIs. Furthermore, it's a significant challenge to link human demonstrations with task-dependent actions. Interestingly, human interaction with GUIs is typically based on visual perception and generic mouse and keyboard inputs, without the need for inspecting the application's source code. We can swiftly learn to engage with new applications that have visually similar interfaces, regardless of differences in their underlying technologies. So, in this paper, we question, can we create an agent that completes tasks for users, relying only on pixel-level visual representations of the GUI state and generic, low-level actions? Learning from pixel-only inputs has proven effective for environments like video games. However, for GUI-based tasks, learning from pixel-only inputs paired with low-level actions presents several challenges. These challenges include understanding the interface layout, recognizing and interpreting visually situated natural language, identifying visual elements, predicting their functions and methods of interaction, and the complexity of mapping between high-level textual instructions and corresponding sequences of low-level actions. As an illustration of this challenge, in the MiniWob benchmark for web GUI interaction, the CCNet model demonstrates human-level accuracy when it has access to both screenshots and DOM structure. However, when the DOM information is removed from the agent's observations, its performance drops by 75%. In response to these challenges, we introduce Pix2Act, a model that uses pixel-based screenshots as input and selects actions based on basic mouse and keyboard functions. Pix2Act builds on the Pix2 struct model, a pre-trained model designed to map screenshots to structured representations derived from HTML. We tune this model using human demonstrations and environment interactions, employing tree search to iteratively generate new expert trajectories for training. We also develop a general browser-based environment framework and adapt two benchmark datasets, MiniWob++ and WebShop, to our setting. On MiniWob++, Pix2Act outperforms human crowdworkers and improves the task score by nearly 4 times compared to previous results. Our findings also reveal that the pre-training of Pix2 struct is vital for Pix2Act's performance. Our main contributions include: 1. We're the first to show that an agent using pixel-only inputs and a generic action space can outperform human crowdworkers on the MiniWob++ benchmark. 2. We've adapted the WebShop benchmark to our setting, establishing the first baseline, although there's still a performance gap compared to larger language models that use HTML-based inputs and task-specific actions. 3. We've demonstrated that pre-training Pix2 struct via screenshot parsing is effective for GUI-based instruction following with pixel-based inputs. 4. We've successfully applied tree search as a relatively simple method for policy improvement for MiniWob++. Section Summary. The paper proposes Pix2Act, a model that can complete tasks for users solely based on pixel-level visual representations of the GUI state and generic low-level actions. The model is trained using a combination of human demonstrations and environment interactions, and applies tree search to iteratively generate new expert trajectories for training. Pix2Act outperforms human crowdworkers on the MiniWob++ benchmark and improves task score nearly 4x compared to the best prior results in the proposed setting. Section 2 Environment. In line with the practices established in the field of reinforcement learning, we consider the interaction with a graphical user interface, GUI, to be akin to a Markov decision process, MDP. What this means is that, at each stage of the process, our AI agent is given some information, which we'll refer to as an observation, and based on this observation, it chooses a course of action. To help our AI agent accomplish this, we've built an environment with consistent observation and action formats, specially designed for tasks that are performed in a web browser. We've used Selenium, a tool that allows us to programmatically interact with the Google Chrome browser, similar to previous studies on web-based AI agents. Now, let's discuss how we form an observation for our agent. We start by taking a snapshot of the current browser window using Selenium, but we don't stop there. We add more information to this screenshot to help the agent make better decisions. Firstly, we superimpose the instruction in natural language on the top of the screenshot, if it isn't already there. Secondly, as Selenium snapshots don't capture cursors, since they are usually displayed by the operating system, we manually add a cursor onto the screenshot. This cursor signifies the position of the mouse pointer. Lastly, we also indicate whether the mouse button is being pressed at that moment. This information proves helpful for instances where the mouse needs to be dragged. So, through this process, we create a dynamic, informative environment that enables our AI agent to make effective decisions at each step, thereby improving the interaction with the GUI. Section Summary. The authors model GUI interaction as a Markov decision process, MDP, and develop a common environment framework with shared observation and action formats for browser-based tasks. They use Selenium to programmatically interact with the Google Chrome browser and form an observation by taking a screenshot of the current browser window, augmenting it with additional information such as rendering. The natural language instruction on top of the screenshot, drawing a cursor on the screenshot to indicate the mouse pointer position, and rendering an indicator of whether the mouse button is currently pressed down. Section Actions. Our actions include basic mouse and keyboard commands, which are illustrated in the given figure. Here, X and Y signify discrete points on the screen. K stands for any keys. M represents optional modifier keys like Shift, and Z corresponds to the amount of vertical scroll, also expressed as a discrete value. Actions such as begin_drag and end_drag allow us to perform click and drag operations. We can adjust the number of coordinate bins along each axis. It's important to note that we don't use any document object model, DOM, information from the environment in our observations or actions. As for our episodes and reward system, an episode lasts until we reach a terminal state or hit a preset maximum number of steps. The environments we're working with give a reward only at the end of an episode. This reward could either be a simple pass or fail based on the task's completion, or a graded reward reflecting the quality of the task's execution. Regarding our agent, we use Pix2Act, which is built on the Pix2 struct model. Pix2Act employs an image transformer encoder and a text transformer decoder, inspired by Vision Transformer and T5. Pix2 struct was initially trained on a task of predicting simplified HTML from screenshots that had visually obscured areas, proving effective in understanding user interfaces in non-interactive settings, such as summarizing screens or captioning widgets. We employ the basic Pix2 struct variant, with 282 million parameters, encompassing 12 encoder and 12 decoder layers, and a hidden size of 768 across all our experiments. This model is used once per time step. Section Summary. The action space for the agent consists of raw mouse and keyboard actions, with a configurable number of coordinate buckets per axis. Episodes continue until a terminal state or a configurable number of maximum steps is reached, with the agent receiving a reward only at the terminal state. The Pix2Act agent is based on the Pix2 struct model, which uses an image transformer encoder and a text transformer decoder, pre-trained on a screenshot parsing task to predict simplified HTMLs from screenshots with visually masked regions. Section Input. The original information in the text indicates that our model takes pixel-based data from the environment as its only input. We also have the potential to include data from several previous observations by merging multiple frames together. However, from our preliminary tests, we found that including past observations doesn't significantly improve performance for MiniWob++, hence we only rely on the current frame in our experiments. We've adopted Pix2 struct's approach for processing images, where we adjust the size of the input images, either enlarging or reducing them, to extract as many fixed-size patches as we can, while still staying within the limit of sequence length. To provide an idea of the resolutions we're working with, for MiniWob++, we use a resolution of 160 by 210 pixels, and for WebShop, we use 800 by 600 pixels. In terms of output, we represent actions using text tokens. These tokens are generated one after the other by the transformer decoder, a process known as autoregressive prediction. We then employ a technique called beam search to produce the top K, most likely actions. When it comes to interacting with the environment, we use a typical greedy policy. This involves choosing the highest scoring action at each step. We've also made one tweak to this strategy. To stop the agent from getting caught in repetitive cycles, we keep track of the actions already taken for a particular observation. Given the current observation, we select the highest scoring action that hasn't been taken before. This small modification results in a noticeable improvement in performance. Section Summary. The model takes in pixel-based observations from the environment and can also consider multiple previous observations. However, conditioning on past observations did not show significant gains in preliminary experiments. The model encodes actions as text tokens and uses a transformer decoder to predict them auto-regressively. A standard greedy policy is adopted for interacting with the environment, with a modification to prevent the agent from getting stuck in cycles. Section 3.1 Training. In Section 3.1, we delve into two strategies for training our models to interact with graphical user interfaces effectively. The first method, which aligns with previous research, involves behavioral cloning, BC. Here, we employ the usual supervised learning methods to train our model, focusing on predicting accurate actions for each observable instance in a series of demonstrations performed by humans. The second method involves the use of reward signals in environments that permit them, where we've observed earlier research employing reinforcement learning, RL, to enhance the performance of the agent. Rather than opting for conventional reinforcement learning algorithms such as reinforce and PPO, we have incorporated a tree search approach for policy improvement. Talking about tree search, it makes use of the deterministic nature of the environment. In simpler terms, it looks forward into the possible results of potential actions to devise a policy that outperforms the strategy of selecting actions purely based on immediate gains. We have used the Monte Carlo tree search, MCTS, which has shown to be superior to simpler search algorithms in our preliminary experiments. This method has been successfully merged with neural network policies in previous studies. Just as in earlier research, we trained a model to estimate a value function. This function provides predictions of the value, which translates to the projected future rewards of a given state. We used a substitute reward system which penalizes the number of steps taken, thereby promoting shorter paths without superfluous actions. The same Pix2 struct architecture used for our agent has been employed to implement this value function estimator. However, we chose to keep the training of these two Pix2 struct-based models that react to the same inputs, separate for the sake of simplicity, even though sharing an encoder between them might have been more efficient. Unlike the agent, this model predicts state values that are assigned to distinct buckets. To determine the value of terminal states during MCTS, we combine the value function estimator and rollouts using our policy that always chooses the most beneficial immediate action. More technical details can be found in the appendix. This enhanced tree search policy can be used to further improve our model through the successful episodes it finds. As this upgraded model in turn results in a more efficient tree search policy, we can keep on improving our model using this technique in an iterative manner. Interestingly, this approach doesn't necessitate any changes to the fine-tuning process of Pix2 Act, as we have kept things simple by tuning based on the episodes from the tree search policy using traditional supervised learning. Section Summary. The paper explores two methods for training models to follow instructions via GUIs, behavioral cloning, BC, and reinforcement learning, RL, using Monte Carlo tree search, MCTS. MCTS leverages the deterministic nature of the environment to determine a more optimal policy than greedily selecting actions, and a value function approximator is used to estimate the value of leaf states during MCTS. Successful episodes found with this stronger tree search policy can be used to iteratively improve the model. Section 4 Benchmarks and Demonstrations. In this section, we discuss the adaptation of two benchmarks, MiniWob GUI and WebShop, to our environment framework. This framework is characterized by pixel-based observations and generic low-level actions. We also applied previously gathered human demonstrations for these benchmarks to our observation and action spaces. Focusing first on MiniWob GUI, it comprises over 100 web browser-based tasks, with each task offering its own algorithm for generating variations and an instruction template. These are controlled by a random seed, allowing for an impressive range of billions of potential configurations for each task. The task instructions are primarily presented as natural language text in the upper yellow section, which can only be visually accessed in our framework. An automatic reward is provided at the completion of the task. Regarding human demonstrations, we used those gathered by a previous study. It's worth noting, though, that the demonstrations from this study were compiled using an X11-based environment, contrasting with our Selenium-based environment. This discrepancy leads to differences in the renderings of the same underlying environment state, creating a gap between the screenshots viewed during training and those seen at test time. Furthermore, we needed to translate their real-time X11-based action sequences into our action space. We managed to achieve this mapping successfully for 59 tasks. However, our Selenium-based environment does not support all behaviors observed in the human demonstrations. For example, Selenium lacks the functionality to highlight text and drag it into a text field, an action frequently used in the human demonstrations for tasks where text is copied and pasted. Additionally, despite our environment framework aiming to cover the fundamental functionality of most web interfaces, some features of certain MiniWob GUI tasks, such as real-time observation of animated elements, aren't supported. Other researchers have also used demonstrations from previous studies, which cover a different subset of MiniWob++ tasks. But these demonstrations lack screenshots or enough information to replay the episodes in a browser environment to gather new screenshots, rendering them unsuitable for our setting. We began with about 1.3 million demonstrations for the 59 tasks that our environment could support. We then filtered out demonstrations that received a reward of less than 0.8, which amounted to about 6% of all demonstrations. Out of the remaining demonstrations, we successfully converted 81% into our action space. We set aside 10% of the data for a development set. On average, demonstrations contain approximately 3 steps per task, although this number can fluctuate significantly across different tasks. Section Summary. The authors adapted 2 benchmarks, MiniWob++ and WebShop, to their environment framework, which includes pixel-based observations and generic low-level actions. They also mapped previously collected human demonstrations for these benchmarks to their observation and action spaces, but faced challenges due to differences in the environments used for collecting the demonstrations. Despite these challenges, they were able to successfully convert 81% of the demonstrations to their action space. Section. Evaluation. In our evaluation, we calculate the average score over multiple random attempts, or seeds, and across different tasks. The scoring system uses the raw reward from MiniWob++, without any time decay, which is originally scaled from -1 to 1. We rescale this to a range from 0 to 100. The score represents the success rate, or the ratio of attempts where the agent secures a positive reward, especially in tasks that have a binary reward system. In instances where the task is not completed because it hits the maximum number of allowable steps, we assign a score of 0. For each task, we average the results over 100 random seeds. Then, we calculate an overall average over 59 different MiniWob++ tasks. Another part of our evaluation involves the WebShop, a digital shopping platform that includes over 1.1 million Amazon products. The goal is for the agent to find and buy a product, guided by text instructions written by a human. This involves submitting search queries, clicking on the search results, and assessing the relevance of various products to the instructions given. The system automatically calculates a reward based on the degree of similarity between the purchased item and the ideal or target product. Section Summary. The evaluation of the MiniWob++ raw reward score, which is equivalent to the success rate, is reported across seeds and tasks. The WebShop task involves finding and purchasing a product based on a human-authored text instruction, with an automatic reward computed based on the similarity between the purchased product and the goal target product. Section. Human demonstrations. In our work, we employ 1,566 human demonstrations, divided into training, development, and testing groups in the ratios of 10-12, 54, and 500 respectively. These demonstrations were collected from prior research. Just like we did with the MiniWob++ demonstrations, we had to adjust the sequences of observations and actions from the original setup to fit our own framework. The demonstrations originally used high-level actions like search or click item, which could correspond to several more specific actions within our environment. In order to break down these high-level actions, we focused on actions that involved a mouse click. For each of these actions, we determined the coordinates at the center of the relevant HTML element. There was a particular challenge with the WebShop platform. Here, due to the web page often being taller than the viewport, the entire content of the screen couldn't always be seen. If a clicked element wasn't within the visible area, we included additional scroll actions until the item could be seen. We converted search actions into 2 separate actions within our framework. This involved clicking on the center of the search box and inputting the search query, then pressing the Enter key. To render the HTML inputs from these human demonstrations, we used our browser to obtain screenshots. We also discovered that superimposing the last 5 actions on top of these screenshots, with each action separated by a break symbol, proved to be beneficial for our work. Section. Summary. The authors used 1,566 human demonstrations to train their model, which required mapping high-level actions to multiple lower-level actions in their environment. They determined the coordinates of clicked elements and added scroll actions if necessary. Search actions were mapped to clicking on the search box and entering the query followed by the Enter key. Screenshots of HTML inputs were obtained using their browser, and the last 5 actions were rendered on top of the screenshot to aid in training. Section. Evaluation. In line with established procedures, our assessment relies on the task score, which reflects the average reward across 500 test instructions. Now, let's dive into the details of our experiments and their subsequent analysis. Firstly, we ran tests on MiniWob++. For this, we honed a single model using episodes from all tasks, culminating in a total of 26,000 steps. We used a batch size of 512, along with input-output sequence lengths of 512/16, respectively. Our learning rate was set to 0.01 and we utilized the Adafactor optimizer for our model. We evaluated our model's performance using a tree search procedure to boost our agent's performance, which entailed performing 2 iterations of policy improvement with tree search. This process led us to collect a total of 826,000 episodes across all tasks, followed by an additional 26,000 tuning steps. Our second set of experiments was conducted on WebShop. For this model, we relied solely on the demonstrations provided by humans for our training data. In this research, we chose not to explore the application of reinforcement learning techniques to WebShop. Past studies have indicated that the benefits of applying reinforcement learning to WebShop are not as pronounced as they are for MiniWob++, which offers a virtually unlimited range of environments with reward signals for training. WebShop's larger resolution and more text-intensive data required us to use a longer input sequence length of 4096. We discovered that it was advantageous to first perform intermediate fine-tuning on MiniWob++. This was followed by an additional 10,000 steps of further fine-tuning on WebShop, using a batch size of 256. Detailed insights into this process can be found in the specified section. Section Summary. The authors report their evaluation using the task score, which is the average reward across 500 test instructions. They fine-tuned a single model on all tasks and performed 2 iterations of policy improvement with tree search, collecting a total of 826K episodes across all tasks. For WebShop, they used only the provided human demonstrations to train their model and did not explore applying RL techniques. They used a higher input sequence length of 4096 and performed intermediate fine-tuning on MiniWob++, followed by 10K steps of further fine-tuning WebShop using a batch size of 256. Section 5.2 Main Results. 5.2 Main Results. We're excited to share the findings of our research using the MiniWob++ and WebShop models, as visualized in figure. In the case of MiniWob++, we provide a detailed comparison between the performance of our model, Pix2Act, and that of human crowdworkers, which can also be seen in figure. Let's put these findings in context. To date, there has been very little research done on these tasks without using DOM and HTML information. When looking at MiniWob++, the only comparable baseline comes from the CCNet model. The creators of CCNet carried out a study where they eliminated DOM information and relied solely on screenshots. As a result, they experienced a performance drop of 75% compared to their original results. However, they didn't provide specific numbers for each task in this study. In an attempt to form a comparison, we've had to estimate the performance of CCNet without DOM information. We did this by assuming a similar 75% performance drop on the tasks we were investigating. Regardless of this estimation, one thing is clear: our Pix2Act model significantly surpasses the performance of CCNet under these conditions. This improved performance is largely due to our novel approach of using screenshot parsing during the pre-training phase. In the case of WebShop, no previous research has ventured into this type of setting. Therefore, we're proud to establish the first baseline for this model. Section Summary. The authors present their model's results on MiniWob++ and WebShop, with task-level comparisons between Pix2Act and human crowdworkers provided for MiniWob++. Previous work on these tasks without access to DOM and HTML information is limited, with only CCNet providing comparable baselines. Pix2Act significantly outperforms CCNet on MiniWob++, largely due to the screenshot parsing pre-training. The authors established the first baseline for WebShop. Section: Pre-training ablations. In order to explore how pre-training impacts our model's capacity to effectively learn to execute commands through graphical user interfaces, GUIs, we examined the performance of our model without the initial pre-training stage. For these specific tests, we only gauged the performance of models that were trained using a method known as behavioral cloning. The data we collected, as can be seen in the referenced figure, makes it clear that this preliminary pre-training stage is crucial for our model to perform effectively. Let's also examine how our model fares without the ability to access information from the document object model, DOM, or HTML, in comparison to previous models that used these resources. These earlier models even exploited DOM information to craft specialized spaces for potential actions. The performance of the best model from earlier studies that used DOM or HTML data can be seen in another referenced figure. When we consider the MiniWob++ scenario, the top performing model here is CCNet, which is trained using both behavioral cloning and reinforcement learning. It has access to both DOM and pixel-based observations. To evaluate CCNet's performance, we calculated the average scores from their reported results for each of the 59 tasks we investigated. Our model, Pix2Act, achieves comparable performance to their best model, even though it only uses a portion of the data that CCNet uses. This is especially noteworthy because we trained both models using a similar quantity of human demonstrations. When we look at the case where each model is trained solely with behavioral cloning, Pix2Act surpasses CCNet, whose performance decreases to 38.7 in this particular setting, though these results are not depicted in the figure. It's worth mentioning that CCNet scores also decline by about 10% when the model doesn't have access to a dictionary of input strings provided by the environment. As we can see from the figure, the key to our model's ability to perform at a comparable level, without relying on DOM-based inputs, is the pre-training using pixel-based information. There's another difference worth noting. CCNet operates in a real-time setting, enabling it to support some forms of interaction not available in our environment, and therefore, can accommodate a broader range of MiniWob++ tasks. However, when trained with behavioral cloning, CCNet doesn't need to deal with changes in the rendering format or the potential for noisy action space conversion. Now, when considering the webshop scenario, the top-performing model in this setting is MiniWob GUI. It uses the HTML source code, a custom action space tailored to the shopping domain, and a larger model backbone known as Flan T5XL. MiniWob GUI outperforms Pix2Act in this setting. Part of this performance gap can be attributed to their use of a simplified high-level action space, direct access to the relevant text on the page, and the ability to benefit from the scale of pretraining and instruction fine-tuning used in Flan T5. However, equivalent enhancements to the scale and pre-training of pixel-based models like ours could potentially lessen this performance gap. In a later section, we go into more detail about other approaches that use DOM or HTML information. We also provide a comprehensive comparison across all MiniWob++ tasks in the appendix. Section Summary. The impact of pre-training on the model's ability to learn to follow instructions via GUIs was studied by evaluating model performance without pre-training. The results showed that pre-training is critical for the model's performance. Pix2Act achieved comparable performance to CCNet, which relied on both DOM and pixel-based observations, while using only a subset of the information and a comparable number of human demonstrations for training. Section. Evaluating transfer across tasks. We're investigating how effectively training can be transferred across different tasks. The idea is that if we use a model trained on pixel data to interact with a graphical user interface, GUI, it could potentially excel at new tasks that adhere to familiar GUI design principles. To test this, we use a model we call Pix2Act, not incorporating reinforcement learning, and see how well it can handle tasks that it wasn't trained on. We set aside 9 out of a total of 59 tasks, training the model on the other 50. These 9 tasks were chosen carefully to ensure they only involve actions or components that could logically be extrapolated from the training tasks. The tasks involve clicking on large checkboxes, selecting colors, navigating to the second tab in both regular and challenging scenarios, identifying shapes, dragging shapes, using a color wheel, and utilizing a slider control. Next, we measure the model's performance on these set-aside tasks, comparing the results when starting with Pix2Struct and starting from scratch. Our results indicate that Pix2Act achieves an average score of 28.3 on these new tasks, as opposed to a score of 65.5 when it is trained on the same tasks. In contrast, the average score is only 7.6 when Pix2Struct is not employed as a starting point. This suggests that pre-training with a common GUI interface can lead to meaningful generalization when applied to new tasks. For another task, Webshop, we found that directly fine-tuning the model for this task, instead of first fine-tuning it on a system called MiniWob++ as previously described, led to a 4.0-point decrease in task score. This shows the benefits of transfer learning across different datasets. Section Summary. The study evaluates the ability of Pix2Act, a pre-trained, pixel-based model, to generalize to new tasks unseen during training. The results show that Pix2Act can reach a mean score of 28.3 on held-out tasks compared to 65.5 when training on those tasks, demonstrating the benefits of combining pre-training with a general GUI interface for non-trivial generalization. Additionally, fine-tuning directly on Webshop without intermediate fine-tuning on MiniWob++ results in a drop of 4.0 in task score, indicating transfer learning benefits across datasets. Section. Tree search analysis. In our analysis of tree search, the data presented in the table demonstrates that by training on episodes created using tree search, we can enhance the performance of MiniWob++. Following an initial cycle of training with these tree search generated episodes, we noticed that the efficiency of tree search itself also increased. This boost can be attributed to the improvements made to the base model guiding the search. Interestingly, we discovered that the most effective greedy policy can achieve results nearly as good as the top-performing tree search policy, without requiring additional exploration or access to reward signals during the inference stage. Our findings suggest that if we were to implement further rounds of policy enhancement through tree search, we could likely achieve even better results. Moving on to related research, our primary focus is on agents that interact with graphical user interfaces, GUIs, like operating system dialogues or web pages, to perform specific tasks. Earlier methods usually depended on structured data derived from these GUIs. This data could vary from a basic list of GUI components and their properties to a comprehensive hierarchical structure of the components, such as the document object model, DOM, tree. This structured data often determined the output space and was typically used for designating action targets, like clicking a specific button. We discussed how such structured information might not always be accessible or might not visually align with what is presented to the users. When the world of bits tasks were introduced, which preceded MiniWob++, a model was proposed that used both visual and structured inputs to carry out basic computer actions, like clicking at coordinates or pressing keys, similar to our Pix2act model. However, this model did not perform as well as humans. Subsequent studies explored specialized architectures for integrating structured DOM information and limited the action space to clicking and typing predefined text on DOM elements. We considered integrating both visual and structured data, as well as a low-level action space that is more in line with human demonstrations. We also looked at the advantages of using large-scale human demonstrations and built upon this research to train Pix2act using a large number of human demonstrations. Our research indicates that Pix2act, a model that relies solely on pixel inputs, can outperform humans on MiniWob++ and equals the performance of top-tier approaches that depend on DOM information. The automation of web-based tasks using large language models, LLMs, has also been extensively studied. For example, WebGPT uses a text-based web browsing environment to search and navigate the web. Recent studies have also investigated using LLMs to create agents that can generalize tasks based on a small number of in-context examples. In other research, raw HTML was treated as a string and fed into LLMs trained on natural language. After fine-tuning these models using demonstrations, they improved the success rate and sample efficiency of MiniWob++ tasks, compared to models that used DOM-based inputs in specialized architectures. In addition to GUIs, there has been extensive research into video game agents that also use visual-only input and low-level actions. For instance, studies on Atari games typically used screenshots as visual input and predicted which controller buttons to press. A study focused on learning from unlabeled videos proposed an agent for Minecraft that uses pixel-based inputs paired with keyboard and mouse actions, similar to Pix2act. Our work is primarily focused on web-based GUIs, as this allows us to employ consistent environmental framework for simplicity. Other research has considered interactive tasks using mobile apps, but these studies haven't typically examined observation and action. Format similar to ours. Section summary. The effectiveness of tree search improves with iterations due to improvements in the underlying model used to guide the search, and the best greedy policy achieves performance close to the best tree search policy without requiring access to reward signals or additional exploration at inference. The paper shows that Pix2act, a model with pixel-only inputs, can outperform humans on MiniWob++ and match the state-of-the-art approaches that rely on DOM information, and other works have also explored visual-only input and low-level actions in interactive tasks such as video games. Section. Pixel-based versus text-based representations. Let's discuss the comparison between pixel-based and text-based representations. When they're accessible, text-based representations can be quite handy, particularly because they allow us to utilize knowledge from large language models, LLMs. The proof is in the pudding, as we've seen amazing results from few-shot learning using LLMs for MiniWob++ and WebShop. However, if a structured source isn't available, we can also leverage optical character recognition, OCR, systems and models designed to predict the location and function of user interface, UI, elements. This connection provides a bridge to harness the power of LLMs. Looking into the future, we see the potential for similar advancements through the scaling and pre-training of vision or multimodal models in a pixel-based setting, thanks to our experience with pixel-based pre-training for GUI-based tasks, even though we've only worked on a smaller scale so far. Our study also aims to go a step further. If HTML or DOM data is not available, we want to contribute to a deeper understanding of how pixel-based representations could be harnessed for instruction following via GUIs. Next, we explore tree search as part of our approach to policy improvement. For MiniWob++, this was dependent on our ability to create new MiniWob++ environments and instruction variations on the fly, while receiving reward signals when a task was completed. However, in real-world environments, both of these aspects may not be possible. In such situations, this approach would need to rely on generative models to produce potential instructions and estimate reward models for task completion. It's also worth noting that we haven't yet conducted a detailed comparison of tree search to other search and reinforcement learning (RL) algorithms. This would be beneficial for a more comprehensive understanding of the most efficient methods for learning from GUI-based environments. Thus, while we've demonstrated that tree search can achieve high performance on MiniWob++, there's still much to explore in terms of search and RL algorithms. Section Summary. Text-based representations are useful when available, as they enable transferring knowledge from LLMs and demonstrate impressive few-shot learning for MiniWob++ and WebShop. However, advances in scaling and pre-training of vision or multimodal models could potentially enable similar capabilities in a pixel-based setting in the future. The approach to policy improvement with tree search for MiniWob++ relied on the ability to procedurally generate new MiniWob++ environment and instruction variations and receive reward signals for task completion, which might need to rely on generative models of potential instructions and approximate reward models for task completion in real world. Section. Broader impact. In the larger scheme of things, our work has been primarily conducted in isolated settings. Deploying our models in real-world conditions, particularly those that interact with third-party services, would need extra precautions to avoid misuse, such as unintentional overuse of these services. The fruits of our labor could pave the way for enhanced user accessibility, increased productivity, and an overall improved user experience. On the other hand, we must acknowledge that our models might inadvertently disrupt security measures. For example, they could potentially outsmart security checks like CAPTCHAs, which are designed to distinguish humans from bots. As a result, it's crucial that any potential security implications of our work be closely scrutinized and considered in ongoing security research. Section Summary. The models were trained and evaluated in offline environments, but caution is necessary when deploying them in environments that can access third-party services to avoid spamming. The research could improve accessibility, productivity, and user experience, but it is important to consider potential security risks, such as agents that use the same interface as humans and may be capable of breaking security defenses.